Hi everyone, I am Jessa Arce, a first year Mama student. Today, I will be tackling the topic rings and fields. Let us first talk about a ring. Let R be a non-empty set with two binary operations. One is called addition and is denoted by plus. Second is multiplication and is denoted by a multiplication operation which is times. R is called a ring if the following conditions hold. First, addition operation of R is an abelian group. An abelian group is also called commutative group. It is a group in which the result of applying the group operation to two group elements does not depend on the order in which they are written. Next, multiplication operation of R is a semigroup. And lastly, it should be linked by a distributive law. So these are the three conditions that should be met for R to be considered as a ring. For both operations and their closure property, addition and multiplication, the set is closed. Under addition, for any AB element R, A plus B is an element R. Well, for under multiplication, for any AB element R, A times B element is an element R. This means if we add any two elements in R, we get another element in R. Similarly, if we multiply any two elements in R, we get a third element in R. In terms of commutativity, for addition, the elements form an abelian group or commutative group. For any AB element R, A plus B equals B plus A. For multiplication, we don't require multiplication to be commutative. In a ring, multiplication may not be commutative. If it is, we call R a commutative ring. Next property is the associative. So in associativity, like addition, multiplication has the associative property. So under addition, for any AB element R, quantity A plus B plus C is equals A plus the quantity B plus C. While for multiplication, for any AB element R, A quantity A multiplied B times C is equals to A multiplied quantity B times C. So for existence of identity, under addition, for any A element of R, there exists 0, an element of R such that A plus 0 equals 0 plus A is equals A. Under multiplication, it does not hold or isn't required. Next is the existence of inverse. In terms of inverse, under addition, for any A element of R, there exists negative A as an element of R such that A plus the negative A equals to negative A plus A equals 0. While for multiplication, we also don't require elements to have multiplicative inverses. Note, rings may not have multiplicative inverses. If a ring does have inverses and or multiplication, then we call it a division ring. And finally, these two operations, addition and multiplication, are linked by the distributive properties. So for any ABC element R, for our first distributive law, A multiplied by the quantity B plus C equals AB plus AC. And for the second operation or equation for the distributive property, quantity B plus C times A equals BA plus CA. So this mentioned information helped us realize and understand the definition of ring. So some examples of ring are the following. The integer z. The integer z with the usual addition and multiplication is a commutative ring with identity. Thus, the only elements with multiplicative inverses are positive and negative 1. The sets QRC or the rational numbers, real numbers, and complex numbers are all examples of rings with identity under the appropriate addition and multiplication. In this, every non-zero element has an inverse. H, or the quaternions. It is a quirky four-dimensional analog to the complex numbers. It is an example of a non-commutative ring. Non-example of a ring is the set of natural numbers. The natural numbers do not form a ring because additive inverse do not exist. Let us come now to field. Let F be a non-empty set with two binary operations. One is called addition and is denoted by plus. Second is multiplication and again denoted by a multiplication operation which is times. F is called a field if the following conditions hold. F under addition is an abelian group. F under multiplication is an abelian group. And of course, it should be linked by a distributive law. So these are the three conditions that needs to be met for R to be considered as a field. Just like a ring, in a field, both operations, addition and multiplications, the set is closed. So under addition, for any AB element of F, A plus B is an element of F. Under multiplication, for any AB element of F, A times B is an element of F. So this means if we add any two elements in F, we get another element in F. Similarly, if we multiply any two elements in F, then we get another element F. So next is the commutative property. For commutativity, under addition, the elements are a commutative group. For any AB element F, A plus B is equals B plus A. Under multiplication, the non-zero elements are commutative group. For any AB element F, A times B is equals B times A. Next is the associativity, or for the associative property. Like a ring, a field satisfies an associative property for both addition and multiplication. And that is, for under addition, for any AB element F, quantity A plus B plus C is equals to A plus quantity B plus C. While for multiplication, for any AB element F, quantity A times B times C is equals A multiplied by the quantity B times. In terms of existence of identity, for addition, we have for any A element of F, there exists zero element of F such that A plus 0 equals 0 plus A equals A. On the other hand, for multiplication, we have for any A element of F, there exists one element of F such that A times 1 equals 1 times A equals A. For the inverses of field, under addition, we have this given condition. For any A element of F, there exists negative A element of F such that A plus negative A equals to negative A plus A equals 0. While under multiplication, we have for any A elements F, there exists inverse of A, which is 1 over A element of F, such that A times 1 over A is equals to 1 over A times A equals 1. Addition and multiplication are linked by the distributive properties. So for any A, B, C element of F, A multiplied by the quantity B plus C is equals AB plus AC. Second, quantity B plus C times A is equals to BA. So here are the examples for field. Some examples are the rational numbers, the real numbers, and the complex numbers. While the non-example of field is the integers z. Integer z does not form a field because multiplicative inverse do not exist because there are non-zero elements without multiplicative inverses. So I have here an illustration for the comparison or the comparison and contrast about the rings and fields. So for the comparison, both rings and field is a set with two operations which are addition and multiplication. For both operations, the set is closed under rings and fields. And another comparison of rings and fields is it's an abelian group under addition. So first contrast between rings and fields is for multiplication, it's under semigroup, while under fields, for multiplication, it's under abelian group. Then another comparison between rings and fields is both operations are connected by the left and right distributive laws. Another comparisons are their examples. So examples which can be found both in rings and fields are the rational numbers, the real numbers, and the complex numbers. On the other hand, under rings, integer z is an element of a ring or is an example of a ring. H or quaternion is an example of a non-commutative ring. Then the non-example of a ring is the set of natural numbers or n, while the non-example of fields is the integers z. So these are all for now. Thank you. Hope you learned something significant.